Sì, puoi partire da prima un attimo.
Per iniziare. Ok, ok, ci siamo Marco. Puoi partire.
Ok. Aspetta un minuto che arrivino un po' di attendees, che sono ancora pochini.
Ok, ok.
We're still waiting a few minutes to gather people in the webinar, and then I will introduce Dima and let him the floor. Okay, I think that we don't need to waste any more time, and let's proceed introducing the colloquium of today. Okay, so as you well know, the research on fundamental physics has always been one of the main focus of physics in general. The typical way of doing that is by means of complex accelerator complex, and I excuse myself for the tricky usage of words, but indeed, I mean, the complexity of such setups has been increasing in the last 60, 70 years or so, since the first cyclotrons have been invented. And nowadays we are operating the LHC, which is a wonderful machine, but indeed is probably the most complex scientific machine ever built. The next step to probe even smaller physics scales would require even a larger machine if we still keep exploiting the same approach to this problem. But the international community has been working on radically different approaches that do not require such large and complex facilities. Okay, so indeed, several groups all around the world have been carrying on experiments of rather small size, the so-called tabletop experiments, with the same goals as the ones we have at the large colliders. Okay, which are of course probing and exploring the fundamental scales of matter and interactions. Okay, so the reason why we wanted to have this colloquium today is indeed to have an overview of this kind of experimental activities, and to, let's say, to show and display the fact that several of these endeavors could actually have even richer physics goals than the LHC itself. Can probe even smaller scales than what we can do at accelerators. Okay, there are even certain things that can only be probed by so-called tabletop experiments, and so on and so forth. Okay, so indeed, and the variety of such experiments is really large, and as you will see from the colloquium today. And we invited for such a review one of the prominent figures, internationally speaking, one of the person who is indeed seen and perceived as one of the top scientists in this kind of scientific research. Okay, so Professor Budker is here today with us, talking about something specific which is related to dark matter, but indeed all these experiments have indeed several fundamental physics applications. I think that most of you already know Professor Budker. Just to give you a very brief let's say introduction to Professor Budker, I just remind you that he's the PI, if you want, the leading scientist of the Budker group. Okay, which shares resources both in Berkeley and at the Helmholtz Institute in Mainz in Germany. Okay, and they are tackling all sorts of fundamental scales problems by means of these, if you want, tabletop experiments. Okay, so Professor Budker is part of the faculty in Berkeley since 1995, and has been a fellow of APS, American Physics Society, since 1904. Okay, and is chairing the topical group on precision measurements of APS, and has been awarded by with several recognitions, among which the NSF Career Award and other things. So I don't want to waste much more time of your time, and I leave the floor to Professor Budker for his colloquium. And thanks since the very beginning for his availability to talking to us today.
Thanks so much, Marco, for this very, very nice introduction. I want to say that with Marco and other organizers, we really tried to make it an in-person event that continued over some months, but unfortunately it didn't happen. But I hope that my talk today will not be so boring that you wouldn't invite me again. And in fact, what Marco said in the beginning gives me already a proposal for something I would be very happy to tell you about. I'm part of the CERN's Physics Beyond Colliders study group on gamma factory, and this is very exciting. I think even thinking about this is very exciting. Is how to turn LHC into something completely different, into a combination of a very unique source of monochromatic highly energetic photons for all kinds of physics, including tabletop, if you want, only with LHC attached, and also to use it as a giant atomic physics style ion trap for precision experiments. So I would be super happy to describe that in the future. But today it's about something else, and it's about looking for dark matter in some new ways, in a sense, although maybe not so. Some of them are not so new for people in Padua, who are very well familiar, and in fact are the leaders in this field. One thing I'd just like to say is that it is not going to be a review of the field. I will mention maybe some other people's work, but mostly I'm just going to tell you about what our group is involved in. So I apologize for limiting the scope to only these things. Okay, so to get started, we have a problem in modern physics, which on this cartoon is shown as an elephant in the room. And this is basically that we don't know what most of the matter is. There is about 5 times more dark matter in the galaxy, apparently, and we have no clue what it is. There are a number of hypotheses of what it could be, but we still don't know. But this is actually not the only elephant in the room. We do not understand why we mostly see matter in the universe and very little antimatter. Then, even though there is more dark matter than normal matter, but the amounts of dark matter and normal matter are comparable. And a priori, why would that be? Why wouldn't there be, 1,000 times more, or a million, or a billion times more dark matter? This needs, but perhaps needs some explanation. We also do not understand really why strong interactions seem to respect the combined symmetry of charge reversal and the spatial inversion, the so-called CP. The theory of strong interactions easily allow CP violation, but it's not seen in strong interaction. That needs to be explained. Then we have some natural scales in physics, like the so-called grand unification scale, or the Planck scale, and we're talking there 10 to the 16 to 10 to the 19 giga electron volt or something like that. And the particles that we have masses that are many orders of magnitude less. Maybe particles that we know range from almost or completely massless to maybe hundreds of GeV, but that's it. It's many orders of magnitude less. So why is that such a hierarchy? That needs to be explained. Then there is the dark energy problem. And I guess intellectually it would be very attractive if somehow these are not, this is not a herd of elephants, if you want, but just one elephant, and all of these different mysteries will be explained in one and the same framework. And in fact, you might say, okay, this is attractive, but is it actually possible? And the answer is yes, and there exist several frameworks that combine the answers. The only issue now is for experimentalists to figure out what is really out there in nature, and that's what we are trying to do. So what can the dark matter be? And there's a long list of possibilities. Again, intellectually, I think it may be attractive to say that maybe there is no dark matter, but we just don't understand gravity. In fact, the evidence for dark matter comes from big things, galaxy clusters, the structure of the universe, and eventually microwave background, and so on. So there's a number of scales, but they are all very large. And how do we know the laws of gravity? We measure astronomical objects precisely. That's the main source for us, and that's on the scale of a solar system. So it would be attractive to say, well, maybe we just don't understand how gravity works on large scales. And there is, in fact, a theoretical framework called MOND, Modified Newtonian Dynamics, that tries to do this. These are extremely subjective phases, and for each of these frowning phases, I must say that there are groups of enthusiasts who enthusiastically reject arguments against these things. So all of these things are alive, but this is sort of, I guess, this, if you would have a vote, which you shouldn't do in science by no means. That's how, I guess, the overwhelming majority of people would vote. Anyway, I myself also participated in an attempt to explain at least galactic dark matter in terms of modification of Maxwell equation due to possible finite photon mass. It was a lot of fun to do this, but we decided that it cannot be the whole story. At least it could be part of the story, but this is not the whole story, definitely. If you measure sort of the how should I say, probability of a candidate being the real thing for dark matter in terms of how much effort is spent, then I think WIMPs are definitely the dark matter, because most for many years the notion of searching for dark matter was basically a synonym for looking for these weakly interactive massive particles, and now some people would say, oh, they're not found and there is no room for that. That's apparently is not true. There is still a very nice possibility for WIMPs, and there is a very nice and attractive theoretical framework to incorporate that. So WIMPs are alive, but they're not the only possibility. So there is a broad class of dark matter candidates, and these are the ones I'm going to talk about today. This is called ultralight bosonic dark matter. And I will explain, I guess, quickly why, if it's ultralight, it has to be bosonic. But first, I'm going to say that depending on the spin and the intrinsic parity of the underlying particle, it could be, for example, an axion or axion-like particle, and this is spin zero pseudoscalar particles, or it could be scalars. One of the popular ones is called the dilaton, that is predicted by string theory somehow. There could be vector particles. These are, in analogy with the photon, are called dark or hidden photon. There's possibly higher spin particles. Now, it is actually very interesting why, if a dark matter particle is ultralight, it has to be bosonic. And the argument goes like this: from observation of the star rotation curves in the galaxy, we can measure, basically, assuming that it is dark matter is really there, we can actually measure the density of dark matter, and it corresponds to something like 0.3.4 GeV per cubic centimeters, or in terms of mass, it's equivalent to 1 proton mass equivalent and about 3 cubic centimeters or something. So if we want to find the particle density, and we assume for simplicity that dark matter is just one type of particle, so all we need to do is take this number, the energy density, and divide by the mass of the particle, and we get the number density. Then let's say these particles are fermions. Then we can do a calculation that we all do in the first year of graduate school. For instance, when we study electrons in a metal, to calculate the Fermi velocity. We do this calculation and we find something interesting. So if the particle is lighter than about 10 electron volts and it's a fermion, then its Fermi velocity would exceed the escape velocity of a particle from a galaxy, and it will just fly away. It wouldn't be confined to the galaxy. So it can be, and therefore, if the particle is lighter than about 10 electron volts or so, it has to be a boson. That's a beautiful thing. Somehow the escape velocity, the gravitational escape velocity dictates to us or tells us what the spin of the dark matter particle is. I find it really fascinating and beautiful. Anyway, so most of my talk will be about this. Maybe if I have time, I'll briefly mention another completely different framework, and it's called anti-quark nuggets. And if normally we think about dark matter as something that interacts very weakly, these objects here interact very strongly. If one of these passes through the Earth, it leaves behind an energy equivalent of a small nuclear explosion. So it's a very fascinating thing. I'll tell you about it if I have time. But first, let me tell you about sort of a family of experiments, I should say, which is cosmic axion spin precession experiments. And I made a little charade here to encode the name of this. So it's cosmic axion. Axiom, as I just mentioned, is a pseudo-scalar dark matter candidate, and the name was dubbed by Frank Wilczek in honor of actually a popular cleaning solution, because axion is actually attractive theoretically because it could solve the strong CP problem that I mentioned in the beginning. And that's why it was introduced, and later people realized that it's also good for dark matter, so it can solve many different problems. Well, this is a spin precession illustration that I'll talk to you about later, and this is actually a picture from our Casper electric experiment in Boston. This is our Casper collaboration, and mostly the experiments are carried out at Boston University and at Helmholtz Institute, Mainz in Germany. But we also have a member from Stockholm University in the collaboration. And Berkeley is involved as well. So the idea of this experiment can be illustrated by this slide. So first of all, suppose we want to find such a particle. What does it mean we want to find it? There is evidence for dark matter, so we can say we already found it through the gravitational interactions. Okay, that doesn't count, right? Because we can't really say what it is if we only measure gravity. So we need to measure some other interaction. So we go to our friendly theorists and ask them how can a pseudoscalar particle interact, and then they write three possibilities for non-gravitational interaction. And one of them is the interaction with electromagnetic fields, represented here by tensor mu nu. And here an important thing is that I should mention as well, that if you are talking about ultralight particles, which are bosonic, you maybe should recalibrate the thinking and no longer think about individual particles, but just like we do it with photons, when we are thinking, for example, about microwave radiation or something, we usually think in terms of fields rather than individual photons. So here we also write this axion field as a sort of as an amplitude A. So this kind of interaction is the interaction with electromagnetic fields, most current searches are actually based on some kind of conversion between axion and photons. For instance, the cavity experiments that are operating in the presence of a strong magnetic field. So the axion comes, interacts with the static field and produces a microwave photon that is then detected with a very good cell phone, so to say, figuratively, as a microwave detector. Okay, but there is an analog of this interaction where instead of the electromagnetic fields, you have gluon fields. This is a very interesting interaction, which is directly related to the fact that axions have something to do with CP violation, actually. What this term generates, it turns out that it generates an electric dipole moment, and it's not a usual, so to say, electric dipole moment that people normally think of as static thing. This will be actually oscillating at the Compton frequency associated with the axion. And there are several experiments that look for it, including the Casper electric experiment I'm going to mention in a minute. And finally, there is another interaction, and that's called the gradient interaction. So see, in these two, you have the field itself, and here you have the gradient of the axion field multiplied by fermion current. On the next slide, I'll show you how to take this relativistic notation and think of it in simple terms. But there are several experiments that look for it, and the pioneering experiment in this area is none other than Quarks, which is actually, in a way, a role model experiment for our activities. Okay, so in terms of our experiments, it's the Casper gradient experiment, and also a network of magnetometers that I will mention that also look for this kind of interactions of axion-like particles. So if you look at these relativistic expressions, and then you take the non-relativistic limit, then you get something very simple. So in the case of the axion-gluon interaction, this Hamiltonian then is just like the electric dipole moment. So electric dipole moment is along the spin of the particle, and this is the effective electric field. So this is just the electric dipole moment interaction of the particle, and this will be in our case nucleons. And the gradient interaction, this thing, if you write non-relativistic form of it, it's just spin multiplied by the gradient of the pseudo scalar, and this object is a pseudo vector, which is very similar, I guess, to magnetic field, because magnetic field is also a pseudo vector. And so this interaction, sigma dot b, effectively, is just like a Zeeman interaction. So it can rotate the spins under certain geometries, as you will see. And so these are our Casper electric and Casper gradient experiment. So I give you a little map of this. So in Boston, the reason the experiments actually separated into sort of different apparatus is because for electric and gradient effect, you optimize the experiment with very different kinds of samples. And so therefore, the actual implementation of experiment is quite different. So the electric experiment is at Boston, and at Mainz we have the gradient experiment. But as it happens, you can use that apparatus to make sort of a modest gradient experiment, and the gradient experiment in the future can also be used as electric experiment. And then we found that, in fact, logistically, we should separate searches in different ranges of the masses of the particles, and we have a high field, low field, and zero and ultra low field experiment. And this one has also branched into two different techniques. I will report on them immediately. Now, there are some experiments that are not part of the Casper program, but are somehow ideologically related. And a former member of our group went back to Hefei, to the Institute of Science and Technology in China, and has implemented a couple of very interesting devices, tabletop devices. One is a maser, another is a spin amplifier. I'll tell you about those, and they turn out to be very competitive systems to look for this kind of dark matter as well. So the origin of the Casper experiment goes back to around 2013, when Peter Graham and Surjit Rajandan, at that time they were both at Stanford, Peter is still at Stanford, called me up and said that they have some ideas about different ways for looking for dark matter, and this led to a day at the blackboard where the details were worked out, and the details turned out to be such that we need to do nuclear magnetic resonance, basically. So I told them, guys, I congratulate you, we invented nuclear magnetic resonance, because our experiment is exactly that. And one of the people on the original proposal, Alex Sushkov, is now the principal investigator of Casper Boston. And for us, it was actually attractive that we were going to look at low mass, low frequency range to complement the searches done by DMX and others. It's a flagship Axiom search experiment. Okay, so how does the experiment work? So the idea is that you have some leading magnetic field that you will eventually scan, and you have nuclear spins that you polarize along the magnetic field. And then if it was a nuclear magnetic resonance experiment, a normal nuclear magnetic resonance experiment, you would apply an oscillating transverse field, and if the oscillation frequency of the transverse field matches the spin precession frequency in this leading field, the Larmor frequency, then the spins resonantly precess away from the direction of this field. So in the Casper electric, we have indeed a static electric field applied perpendicular to the magnetic field, and then this dipole moment that's induced by the oscillating axion field. And so then the interaction that we have here is just equivalent to transverse magnetic field, and again by tuning the leading field, so the frequency of the Larmor precession is equal to the frequency of the oscillation of the axion field, you get on resonance and should see spins flipping without any application of the transverse oscillating magnetic field. In Casper gradient, that was previously known as Casper wind, we don't like that term anymore. I can explain why. I said that the gradient of the oscillating axions is just a magnetic field, so we don't need to apply any other fields, and we just have an oscillating magnetic field due to dark matter itself. And again, we scan the leading field and we watch for the spins to flip. And when the spins flip, we detect it in some way at high frequencies. We can do inductive pickup as in normal NMR, and at lower frequencies we can use squids to detect this oscillating or precessing magnetization. So that's the idea. So we are very excited because just a few weeks ago, after several years of building the experiment, we have the first results now from the Boston experiment, and we have a sample there. It's maybe 5 millimeters or so with typical dimensions, and it is a ferroelectric crystal, PMNPT, and the reason we want a ferroelectric is so that the nuclei, lead nuclei in this case, inside of the sample, they are subject to an effective electric field produced by this crystal, and this is inside a magnetic field. And then we do what I said. We just scan the magnetic field and watch for spin precession. Now, this experiment is actually not so simple because this is a system with very high inhomogeneous broadening of NMR lines, and there is a lot of sort of NMR you need to understand. So a lot of the experiment consists in actually doing the NMR and characterizing the spin behavior in this system to understand it before we look for dark matter. But okay, so after this step is done, then the actual dark matter searches occur, and this experiment, as I mentioned, is the first one, in a sense, a proof of principle of the concept. By the way, you will see a lot of these diagrams in my talk and any other talk on ultralight bosonic dark matter, where on this axis you typically see the mass of the particle in electron volt, and this is the corresponding Compton frequency of the particle, and here you see the values of the coupling constants. And on these plots you also see this line. This is usually marked as QCD axion. This is the sort of most attractive part of the parameter space, because here lives the axion that also solves the strong CP problem. So remember, we want to get as many elephants as we can in one go. And so the important thing to see here is that, okay, so this is an experiment that this is our prediction. It shows that, yes, in a narrow range of frequencies, we understand things. And the other plots here show how we're going to scale it up in the next few years. And in Casper Electric, we actually hope to reach the QCD axion line, and this seems realistic now. I see that I'm kind of short on time, so I'm going to accelerate a little bit. So this shows various avenues for progress in Casper Electric in more detail. Okay, so in the meantime, at Mainz, we were building a Casper gradient, and while we were building that in the lab adjacent to Casper, we were doing something rather different. It's something that's called zero and ultra low field NMR. I'll tell you a couple words about it. And originally, we didn't even think of using it for dark matter searches, but then we realized that indeed it is quite possible to use those experiments, and we've done a couple of them. And in fact, this turned out to be the first experimental results from the Casper program actually, and they were published already in 2019. And they looked quite competitive with other people in the field. And while doing them, we realized something, that once you go to the lowest possible masses of Axiom here, you have to be very, very careful. And so first of all, I need to tell you why this plot stops here and doesn't go further. If you take a particle that has this funny mass of 10 to minus 22 electron volt, and you calculate the de Broglie wavelengths for such a particle, you will find that it is bigger than the galaxy. And because the dark matter has to be somehow confined to the galaxy, it cannot be bigger than the galaxy. This kind of gives a cutoff around this range. But you know, if there is a mass of the underlying particle, then the total energy of the particle is mc squared. This is the rest mass, plus these particles are non-relativistic, okay, because of course the escape velocity from the galaxy is non-relativistic. So the total energy is mc squared plus mv squared over 2. And the maximum that this V can be in the galactic frame is on the order of 10 to minus 3c. So you can see that the total energy of all axions has to be sort of within 10 to minus 6 or so from the rest energy. And this says, as always, when you have a spectral line, if you want, so this spread in frequencies sets the effective decoherence time. And as I just explained, it's about 10 to the 6. So here in this range, if you look what the corresponding frequency of oscillation of dark matter is, it's about a year. And so the coherence time is about 1 million periods. It's 1 million years. So this brings the following horror scenario in. So imagine that you do your experiment and you don't see any dark matter. Then it may be because there is no dark matter in this frequency range, but maybe you are just super unlucky and this sort of chaotic dark matter that has this kind of speckle-like pattern that changes over the time of 10 to the 6 periods of oscillation. Maybe you were just very unlucky and you were measuring in a time when it's in a local minimum. And then you have to wait 1 million years for it to come out of that minimum. So this is a problem specific for the experiments that take measurements at times that are shorter than the coherence time. For most of the range with higher frequencies, this is not a problem at all. Anyway, so we realized this, and we realized that you need to be really careful and do special analysis here statistically to set the limits on dark matter that I described in this paper here. Zero field NMR, how does that work? So in normal NMR, you want to go to as high a field as possible. This is all upside down. So we have, instead of that, a multi-layer magnetic shield because we want to make the field as low as possible. These days, what we do is we like to hyperpolarize our spin by some clever method like dynamic nuclear polarization or parahydrogen or something like this. But there's also like a straightforward technique. You actually have a magnet above this. You put your sample in the magnet, it polarizes, then you drop it and you do your experiments. The reason we want to have zero field is that we want to be in this regime where actually we turn off the Zeeman interaction, and what remains is the spin interaction, like in this formic acid molecule. So you have then two spin 1/2s here, one from carbon 13, one just from proton, and they can add into either total spin 0 or total spin 1, so a singlet and a triplet state, and then you can manipulate these states and observe actually transitions at the frequency of this spin interaction. In the case of these molecules, we're talking about 200 hertz or so. And how do you use it to look for dark matter? In a few words, so in the absence of external magnetic field, you just have one resonance line. Now you apply a tiny magnetic field, to split these levels, and you now have this a doublet here. And now if you apply also on top of that a bit of an oscillating magnetic field, you see the sidebands appearing. So the idea of the experiment is that we do not actually apply an oscillating field, but we look for dark matter applying this effective magnetic field to give us sidebands. So it's an interesting question. So here we operate in the regime of fairly long coherence times, where one individual measurement that lasts for the coherence time of the spins here about 10 seconds is shorter than the coherence time, and then we're actually able to combine many measurements, so effectively prolonging the coherence time of the experiment. Maybe I will not bore you with the details. And so this was possible to do this. And this led us to results on limits for gluon coupling, and also for dark photons and quadratic interactions. Now, let me just go back and give you one interesting detail here. So, so this works very well for frequencies where you can nicely resolve the sidebands. But if you want to go to much lower frequencies, then there are no sidebands, but basically in that regime, you will have these lines moving very slowly here. And then the question is, how do you distinguish the signal? How do you distinguish the signal from slow drifts of magnetic field in your shield, for example? And we had this idea of comagnetometry. So all precision experiments basically use some kind of a comagnetometer device in it. And the idea is that this comagnetometer should be sensitive to magnetic field drifts, but not to the exotic effect you're looking at. And then comparing, whereas the system that is looking for the exotic effect is sensitive to both the magnetic field and the exotic effect. And then combining these, you can separate your exotic effect. But the problem is that you can never really combine your comagnetometer with the sensitive system in one place. So we had an idea of doing this sort of in an ultimate way, where we use one and the same molecule, and we just use different transitions in different molecules where the sensitivities to the magnetic fields and the exotic interactions are different. And we checked that it works. And in fact, with this technique, we were able to go all the way down to this 10 to minus 22 electron volts, and that's why you see this couple of different regions. When we have done and published this work, we immediately realized that we can improve the sensitivity by about 4 orders of magnitude or so by actually going to hyperpolarized samples. But now I'll show you that there is even potentially a better approach to this in this frequency range. Okay, so I have a question to Marco. I have to stop at 4 p.m., correct?
Dima, I believe you can carry on a little bit more if you need more time. Do not rush.
Yeah. Okay. All right. So thank you. So here I want to say that in the meantime, so that was published in 2019, and in the meantime, a couple of things happened. First of all, there is a very interesting paper by these folks who have actually taken some published data from Romali's group from some magnetometer devices, and they have made an analysis, and I'll show you their limits that are very impressive with this. And the other thing that happened is that my colleague Jiang Min built this spin amplifier, and I'll show you the results of that work in a second, and that actually already reaches the limits that were projected here. Okay, but this in a sense was a little side experiment, and in the meantime the main Casper program excuse me, is being carried out. So we have a magnet. This is probably the world's lowest field superconducting magnet here. It's a wet bore system, and the sensitive element here that we have is hyperpolarized xenon 129, which was chosen for the best combination of relaxation time and the ability to hyperpolarize it. And these experiments are basically beginning now. And in the meantime, we are waiting on the arrival of a bigger magnet, 14.1 Tesla, which should be here by the mid-year, and that will allow us to go all the way here to higher frequency ranges. Okay, so this is what I mentioned already. So this is Jiang Min and another student, Haowen Su, and these guys work in the laboratory of my close colleague, Professor Xinhua Peng at USTC. And this spin amplifier, in a sense, is a simple device. It's an atomic vapor cell, or a few centimeters in diameter, where you have a mixture of rubidium and xenon. And when you optically pump rubidium, you transfer the polarization and collisions from rubidium to xenon. And then xenon acts as a sensor for your dark matter field. And when it is resonant to the Larmor precession of xenon, xenon atoms, xenon nuclear spins precess, and they are then read out by rubidium. And the advantage of this scheme is that this is a very efficient way to polarize and read out, because there is this thing called contact Fermi interaction between the rubidium electrons and the xenon atoms, so this coupling is strong and allows you to very efficiently read out what the xenon atoms are doing. And so the first experiments were just submitted, I think a week or so ago, to the archive, and you can see that they are really quite impressive. So these were our results for Casper Zulf, and this is now a result a run where it's about 100 seconds per point, and if you sit for 5 hours on one point, you can even go further. So this is a very significant progress there, and this is the magnetometer reanalysis that is even better here in this range, but you can see that the spin amplifier extends further. So it's very, very exciting result, I think. All right, so I think I have a few things to tell you, but I think I'm going to now go into the regime. I took longer, I'm sorry, telling you about Casper and related experiments. So now I'm going to go in the regime where I'm going to tell you what I didn't have time to talk about. Okay, so one of these things is our Wrestle experiment, and as you will see, it stands for a weekend Relaxion search laboratory. It's actually now longer than a weekend, but this goes back a few years to a suggestion by Asimina Arvanitaki that dilatons, which are scalars, could be a dark matter, and the way you can find their manifestation is that they should effectively change the values of fundamental constant. And so you may recognize Francesco, which makes a cameo appearance in this photo, by the way. So I really like this photo. Asimina and her friends, they had this proposal that led to basically all atomic clock laboratories starting to look for these kind of oscillating fundamental constants. Before, people were just looking for temporal drift. And actually, our group was the first to start doing this. We used atomic dysprosium, and now every laboratory is doing this. In the meantime, there were also very interesting developments on the theory front, and these guys have introduced something that's called Relaxion. This is a beautiful play on words. It's an axion that's undergoing relaxation oscillation. And Gilad Perez from Weizmann Institute has sort of taken this idea into some interesting directions, which I don't have time to talk about. But what Gilad told us made me extremely excited. He said that, in fact, with these relaxions, it is possible that these particles can simultaneously have pseudoscalar interactions, so affect the spins, but also effectively affect the fundamental constants, and so they can be basically at the same time scalar and pseudoscalar. And so this motivated us to start looking for them, and this is Gilad's sort of favorite range of the masses. So with my colleagues, we had an idea how to do this, and we thought it's going to take a weekend. This looks a little complicated, but in fact, every laser undergraduate laboratory has setups about this complexity. This is what's called Doppler free saturation spectroscopy that allows you to do optical spectroscopy of atoms and get rid of the Doppler effect. And we set this up. We fairly quickly got to the level of a few times 10 to minus 15 in the relative variation of optical frequency. So the idea here is that you take your laser and you lock it to an optical cavity that cannot effectively respond to variations of fundamental constants. So it's like an anchor, and an atom can respond. And so the atomic energy levels are doing this kind of dance, and you should be able to see it with this apparatus. We published it, and now we are improving it. This is already outdated. We have crossed the 10 to minus 18 line, so it turned out to be a pretty nice way of doing things, and this is being extended in collaboration with a group of Stefan Schiller to also molecules. So this is sensitive to, if the original experiments are sensitive to the variation of alpha, fine structure constant, and electron mass, the molecular experiments are also sensitive to the change of nuclear mass and strong coupling. So this turned into a pretty exciting field. That actually requires some theoretical thinking, and I'm going to skip that. I'm just going to say that fast oscillation of fundamental constants are need to be thought of somewhat differently compared to slow drifts of fundamental constants. For example, when you're talking about slow drift, you cannot really say that any constant that has dimensions like speed of light or the mass of electron can change. But if you have oscillations faster than the sum of the time scales in your experiment, you can talk about this individual constant variation. And no time to say more about this. I mentioned briefly that there are networks now of sensors looking for dark matter. There is a network of magnetometer called Global Network of Optical Magnetometers for Exotic Physics Searches. It's submitting a major results paper as we speak. It's a very exciting project that started as a search for a fairly esoteric thing, the dark matter or axion-like particle domain walls in the universe, which is now looking for all kinds of interesting exotic events. The science case has expanded because we are realizing that there are many things this is sensitive to. There is an interesting hypothetical scenario that there is some weakly interacting matter that is suggestively drawn here as an elephant that's trapped in the Earth. And because it's weakly interacting, except for gravity, it can undergo oscillations near the center of the Earth. And there happens to be an exquisitely sensitive network of gravimeters, superconducting gravimeters that are there to study the Earth that can look for this. And a couple of groups, including ours, has done this analysis. This is a fun thing to do. There is a possibility. There are very few places where you have antimatter, but at CERN you can find antiprotons that are trapped in traps for many months. And with these antiprotons, you can also do this sort of spin precession experiments. And this was done by the BASE collaboration. And in collaboration with my then postdoc Evgeny Stadnik and myself. And this was an exciting thing because it provided the first search for dark matter using antimatter as a probe. And there are some exotic but very interesting scenarios of asymmetric interactions between matter and antimatter with dark matter. And so antimatter probes are very interesting. Okay, I will have some shame, I guess, because I'm already 5 minutes over, and I'm not going to tell you about Axiom quark nugget framework unless you ask me in the questions and answers, and then I'll be happy to tell you about this and how we look for them. Instead, I'm going to summarize that. I guess I spent most of my time talking about the cosmic axion spin precession experiment, Casper, and gave you the first results from both Boston and Mainz, and told you a little bit about spin-offs. And then I told you about the Russell experiment a bit. In conclusion, we have these big problems that I call elephants, I guess, in physics. But even more than we have problems, we have nice ways to look for possible solutions for them with networks of sensors with all kinds of NMR, including exotic NMR with atomic spectroscopy, with antimatter probes, with gravimeters, with seismometers, with spin amplifiers. And the conclusion from this is that dark matter has nowhere to hide. Thank you.
Thank you very much, Dima. That was indeed an impressive review of very interesting and intriguing experiments. Now it's time for questions for you, and I invite the attendees to ask them. I actually apologize already in advance because I'm not 100% familiar with this webinar way of let's say transmitting of Zoom, and therefore I'll try to deal with it as best as I can, meaning that people are not allowed to speak up unless I allow them to do that. Otherwise, they can write questions on the Q&A session. In the case, I will ask the help of my colleagues from the multimedia team.
There is seems to be a Q&A. No.
Yeah, there's a Q&A button which allows people to write down questions. But okay, there. Wait. Okay. So, Katerina, if you want to ask the question, I think you can answer live. Hold on. So, listen, for the time being, I will simply repeat the questions that I get from the Q&A. I think you can read them, but I can do that myself for the rest of the people. So, Katerina Braggio, she's asking you whether you can give us an idea of the challenges involved in improving the sensitivity in Casper, especially the Boston version.
The challenges are well. The challenge, okay. There are challenges definitely. So apart from understanding NMR in this material, a big challenge here is. Excuse me, I'm gonna just scroll to that slide. So a big challenge is that we need to get hyperpolarization of a solid sample, and this is not a trivial thing to do. So our idea that we are pursuing is that if you take this sample, and actually Katarina is an expert on this kind of thing, so if you have advice for us, that would be very helpful, Katerina. So, but what we're thinking about is producing transient paramagnetic centers that we would be able to optically pump, and then the polarization would be transferred to nuclei. And then, because these centers are short-lived, they will go away, and the nuclear polarization that lives longer will remain, will stay. So this is what we're trying to do. We already can control relaxation times with such centers. So this is already a useful tool for us, but no hyperpolarization yet. That's what we're trying to achieve. So I would say that's probably the one challenge that still needs to be addressed. For the other things like low noise amplifiers and this and that, this experiment is currently limited by the amplifier at 4 Kelvin, but there are ways to address that. It's clear, but hyperpolarization is a major challenge.
Okay, thank you, Dima. Other questions? Yep, there is, I believe, one. Okay, no, it's simply Katerina thanking you.
Yeah.
So while other colleagues are thinking about questions, I have actually one myself, one curiosity. The gravimeters themselves, it's actually the first time I hear about that. Can you tell us a little bit more?
Yeah.
What they are, how they work, and what's the principle that they rely on, and so on?
Yeah. Okay. So first of all, I should make a disclosure that so here's, I think, a gravimeter here. So we have nothing to do with the sensors themselves. So this is the geophysical basically network that has been operating for 40 years or so. And the nice thing about them, if you go to these websites, you can eventually get to the data that they stream. And so what we have done is we have analyzed the data kindly provided by them. Actually, we have also a collaborator working with this network that was helpful as well. But the idea for these gravimeters is, I guess, you have a superconducting ball that you levitate, and there are feedback coils that keep it sort of at a fixed position. And there is an amazing thing about their sensitivity. They one instrument, its intrinsic noise is 10 to minus 12 G per root hertz. 10 to minus 12 G per root hertz. It's unbelievable. It's some of the most precise instruments I know about, and these have been in operation since the 1960s or something. It's unbelievable.
Wow, that's impressive indeed. Okay, other questions for Dima?
So in the future, the atom interferometers are currently a few orders of magnitude behind in sensitivity, but they are catching up. In principle, when yeah, they may have certain advantages eventually.
Okay. So I don't see any other questions for Dima. I think it was indeed quite an exhaustive review of very sophisticated experiments, indeed, and which requires very very advanced technology. Okay, so yeah, I think that we don't have anybody else willing to ask questions. So Dima, actually, let me take the chance to indeed iterate on what you said at the beginning, meaning the part on the gamma factory, which, as you know, I'm very much interested in. So indeed, if we have the chance to have you here in person whenever the pandemic is over, or at least is allowing us to travel around, that would be very nice to have you here and discussing about those things, because indeed I think that that is a very promising and exciting challenge and experiment.
Thank you. Padua is full of friends and colleagues and interesting physics, so I will be delighted to come
Okay.
as soon as possible. Okay.
So indeed, I mean, let's hope that you will get the chance to visit us not too far in the future. And in the meanwhile, let me thank you again for the very nice and instructive colloquium. And okay, also on behalf of the organization, let me thank you again. And as I said, see you soon.
Ciao.
Ciao, bye bye.